Good morning, good afternoon. I'm Rob Blomquist with the NVT Group companies Data Physics and Lansmon. Thank you for joining today's webinar on modal analysis, impact testing with the Data Physics 900 series analyzer. So today we have two distinguished modal analysis experts leading the presentation, Kalyan Vitta and Jim Steedman. Both Kalyan and Jim attained their master's degrees in modal analysis from the University of Cincinnati. Kalyan is product manager at Data Physics, responsible for the Data Physics Analyzer product line. And Jim is with Navcon Engineering, a noise and vibration consulting firm located in Fullerton, California. And with that, we'll turn it over to Kalyan to start things off.
Thank you, Rob. Good morning, everyone. Modal analysis involves several steps. In today's session, we are going to talk about how everything comes together, starting with a technique called impact hammer measurement. Following that, we would look at the modal parameter estimation with MEscope and FEM-Test correlation with FEMtools. We would like to maximize the time on the actual measurements, showing you the user interface of the 900 series. So we'll try to get through the PowerPoint slides as quickly as possible. 900 series hardware have two flavors. The first, the Abacus 901, which is shown on the top right side. It goes up to 6 input channels. And the last two BNCs here are called the flexible channels. That means the two channels, the two BNCs can be programmed and configured as inputs, outputs, or tags, depending on your test requirements and application. The 901 can operate in standalone mode. That means you can initiate a test and simply disconnect from the computer and walk away, and the system will start acquiring data, and you can also set it to stop automatically, or you can come back and connect to it and control the test. Multiple 901 units can be combined together. So for example, if you have 3 901s, 6 channels each, you will get a total of 18 channels. On the bottom left here, the Abacus 906 can go up to 36 channels. Similar to the 901, the last 2 rows of the BNCs in each column can be configured as inputs, outputs, or tags. So the 906 flexible channel configuration allows you to do that. This would expand the measurement capability depending on your needs. And the 906 comes with a 500 GB solid state drive inbuilt into the system. Again, as with 901, you can combine multiple 906 units, or to make over thousands of channels, or you can combine 906 and 901 units together as well. On popular demand, we made the Quattro hardware also compatible with 900 series software. That means if you have a Quattro, you can simply add the 900 series to be compatible with 900. And Quattro is USB based. The only connection that the Quattro needs is a USB connection, and Quattro can go up to 4 inputs, 2 outputs, and 1 tag. All the 3 systems, the 901, 906, and Quattro, are loaded with standard features. They come with high frequency, over 200 kilosamples per second, high voltage, over 10 volts, all the way up to 30 volts. If you're trying to measure high voltage measurement, certainly you can do that with these units. Also included 51,200 lines for high resolution, and the zoom measurements, sensor calibration, TED support, and sensor database are all included as standard features. There are different analysis types, starting with FFT analysis, the regular FFT analysis, recording and playback analysis, structural analysis, including your transfer function measurements, MIMO measurements, demodulation, RPM analysis to synchronize the data to the speed of the rotating shaft, real-time octave analysis, shock response analysis to characterize shock data, and all these are the conventional measurement types. Also included are the recording editor, which would allow you to resample, filter, concatenate data in the 900 software. Multi-measurement and multi-recorder capability allows you to combine two different test types. So in a multi-measurement, you can run auto power spectrum and a transfer function simultaneously at the same time. Or you can record at two different sampling rates and export to different export formats at the same time. Also, we have channel math capability to create virtual channels to help with the application in terms of if you want to add channels or subtract channels, you want to make a resultant, you don't have to do this external to the software. It's all inbuilt into the software. As I said, we are planning to switch to the software as fast as we could. Modal analysis is the process of identifying and analyzing a structure in terms of its natural characteristics, being frequency, damping, and mode shapes. I have a similar arrangement on my side here with one of the channels connected to the impact hammer and the other channels connected to accelerometers. A typical measurement, we would be interested in the response, but in a frequency response measurement, we are interested in both the response as well as the stimulus or the reference exciting the structure. Broadly, there are three excitation mechanisms using an impact hammer as shown here, or using a shaker, or natural excitation of a structure. So with that, I'm going to switch to the software here. When you first launch the software, the 900 software that is, you will see a screen similar to this, showing all the test types at a glance. And the software itself has 4 functional areas, starting with manage test, run test, review, and system configuration. And the reason for this distribution to efficiently use the time while you are running a long duration test in the run test area, you could be in the review mode, you could be reviewing the data, creating reports, exporting data at the same time while your test is ongoing. Let's jump to system configuration for a second. System configuration would show you the units or the systems that are connected at the present time. So in my case, I have a 901 connected, which is shown in the first box here, and the next one is my computer. As I said, the 901 has flexible channels. So just to give you an idea, I configured the 901 with 4 input channels with an output and a tag, or I could have configured it as all 6 input channels. Let's go back to manage tests and let's see if we can run an impact hammer test. Under manage tests, I'm going to click on the new test. Under new test on the left side, I can select the measurement of interest. If I'm only interested in the response, I would go for something like an auto power spectrum. And on the right side, you can see all the various templates. The templates is a way to get to the test, the required test as quickly as possible. So if you have a template already set up, it would take less than 10 seconds to be up and going. The same concept for all the different test types. You can create your own templates and you can select and seed the next test from that template. For example, I'm going to select the impact hammer test template. And let's call it impact hammer measurement. So once you click OK, you will see the setup has 3 tabs, starting with the test tab, channels tab, and transfer function. The test tab includes all the documentation in terms of you can assign a project, you can assign a customer or a test article. There is a lot of space for test description. You can add mandatory run notes. You can select the run increment, choose how to increment the test. Under channels, there are different radio buttons. We'll start with the front end, and I'll show you how easy it is to configure your test. So let me go ahead and type in. So I'm doing this quickly using my arrow keys on my keyboard. And for channel 1, as it is connected to a ICP hammer, I'll select ICP. I can select my ranges and I'll go up here and select it to be 10 millivolts. And on the units, I'll simply type in pounds L, and because of the database structure, it would give me the choices pound force right here. Now I configured my input channel 1. If I take my mouse and select for channels 2 and 3, I can highlight them and select change the manual to TETS because I have connected channels 2 and 3 to TETS type sensors. Once you read TETS, even if you have 36 channels or 72 channels, however it may be, you can simply select TETS. Once they are connected to TETS type, you can simply read TETS to populate the sensitivity and the engineering units. Now let's go to transfer function. So under transfer function, a lot of parameters are already defined because we started with a template. Stable 4 averaging for this particular test, preview averaging is already selected. For this particular test, I'm going to select a different bandwidth. And one of the unique features, differentiating features of 900 is you can simply type in any value you would like. So in this case, I'm just typing in 2000 and I could easily type in 1900 if I want. It would take any bandwidth. Under the windows, I'm going to go ahead and select force and exponential window. And you can see that everything is laid out here on the same screen. So let me go ahead and change this to, for example, 0.2. And for channels 2 and 3, select it to be 0. And all my signals that are available in this particular test are listed here. And under saves, I already set up in the template to export it to MEscope. That's what we want to do. And also to ASCII at the same time. All right, with that, let's go ahead and take a quick test. Let me go ahead and initialize this test. As you can see, all the parameters are at your fingertips if you want to fine tune them. All right, so once I initialized it, let me go ahead and click on start. As this is a triggered test, it says waiting for trigger. So let me go ahead and take my first impact. There you go. That's my first impact, and you can see on the layout or on this page, the top graph shows our transfer function or the frequency response function, which is nothing but the ratio between the response and the reference. On the left side, on the bottom graph here, that is the impact in time domain, the hammer impact. And the middle graph here shows the energy of the hammer in frequency domain. So let me go ahead and change that to dB. It's a good idea from the flat portion to, you can see that it's tapering off. So the thumb rule is for your measurement of interest, it should be from the starting point to the ending point. If it is around 15 dB to 20 dB, that means you're exciting the resonances within your bandwidth of interest without exciting the resonances outside the bandwidth of interest. So that's a good thumb rule to follow. And here is the exponential decay of channel 2. So I'm satisfied with this impact, so I'll go ahead and say yes. All right, so now as we set up to 4 impacts, so let me go ahead and take another impact here. Right, that seems to be overloaded. All right, that's my second impact. Right, once I'm happy about that, I can click on yes, and you can also see at the bottom the point direction info. If you want to change the point direction information at any point, then you can do that here as well. So let me go ahead and take one more. All right, 3 frames and one last one. So once I take all the 4 frames, so let me go ahead and click on yes. That is my first point on the structure. So as I said before, we have the run and the review. So I'm going to go into the manage tests and go to my demo impact hammer measurement and double click on the run one. So it would take me to the review area where I can look at the transfer functions in real imaginary, all the different formats, the coherence transfer function. And once I'm happy with that, I just simply close that and go back to my run test area. Now I'm going to go click on start again. Now I'm going to the next point as I programmed it to auto increment. So now I'm going to current point number 2. Now I'll go ahead and take impacts at a different point. I want to show the under preview capture window a feature called auto accept. Under auto accept, if you are closer to the structure and working away from the computer, you can set up an auto accept feature. And I moved my mouse away. So if I take my next impact, in about few seconds, it would auto accept the measurement. All right, that's the last one. So you have to make sure that you have enough time so that if you actually do a double impact or a bad impact, you can go to the screen and say no. All right, with that, I'm going to go into the manage. With that, I'm going to click on end. And close the test. So here is my test, And if I go into run 1, I have only 2 points. So you can actually see my 2 points at 1x and the another one at 2x. So if you have a big structure, you could be having a lot of points that you have to traverse from one point to another point and look at all the different points. All right, let's go ahead and close this. Now back to the manage tasks. So under manage tasks area, I have all my tests. I can hover my mouse on a certain test and I can actually see all the important parameters that are set up for that particular test. This helps me in choosing the test easily, or I can go to the global search area and I can simply type in my keyword, so it would, fine tune and narrow down my search. So in this particular case, I would go into my measurement and I would select my transfer function here to filter all the measurements to a TRF type of measurements. Under here, I have different tests. So let's go ahead and see what I have under Jim Beam analysis. And this one was particularly done with a shaker excitation. Under the first page, if I go in here, you can actually see that the excitation that was used is a burst random signal. We talked about different formats, so you can certainly look at the frequency response function in different formats, real, imaginary, Nyquist, or even octave formats. So depending on the structure, you can use the impact hammer, and if it is a big structure, you have to use a shaker excitation. We said we will look at also, maybe a full modal survey. So let me go into run 10 here. So this was done on a bigger structure, and you can actually see how easy it is to traverse through different runs. So I'm under run 10. I can use this arrow to go check out a previous run. This is run 9, run 10, and these are all the different saves. It makes it so easy to go across runs and between saves. Or I can click on this view runs and go to a particular run of interest. For example, let me go to run number 7. So run 7 has about 34 saves, and each save represents and corresponds to a point on a structure. And I can highlight my mouse and easily travel, go through all the different saves here using the up, down arrow keys on my keyboard. So I'm looking at focused FRF measurements, or this is under the mode called single select. If I want to do a comparison, I can simply change that to multi-select view. The multi-select adds a checkbox in front of each saves, and so I can simply right-click on them and select all of them, and you can see how I can overlay all the different saves on one picture and look at that as a kind of a big picture bird's eye view. Or I could start eliminating some of these saves just to see if there are any outlier points that I don't want to include in my display. I can simply do that. Or if I want to, let's say I want to focus, as an example, I want to focus on the first top 10. Let me go ahead and unselect, and I can start clicking on the first 10, or even better, because of the database format, I could go into the save filter, and it allows me to add a filter. So that means I'm just selecting the top 10. Now I'll right click on it and I would select visible. Select visible only applies to the filtered saves. Now I have the top 10 filtered saves. Now we designed the system so that all the parameters that you use, all the tools or the commonly used tools are at your fingertips. So I can change my formats very easily from this drop down. I can change, I can display real, imaginary, magnitude, phase, all the different formats. In fact, I could go up here and select the waterfall. So waterfall is a nice view wherein it would take the saves and it would display it in waterfall format. So this is not particular to a transfer function. If you're using in any measurement, power spectrum or any other measurement, you can take the saves and display them in waterfall format. Some fancy waterfall formats here. We can display them in spectrogram. We can display them in Campbell. Campbell format is represented using circles. The bigger the resonance, the bigger the circle on the display. Let's go back to our waterfall here. And as with any graph in the data physics systems, you can right click and copy the graph, or also, in fact, you can copy the data from the graphs using the copy all traces. If you copy all traces, you have the data onto the clipboard. You can paste it into Notepad or Excel. All right, let's go ahead and close this. Let me go back to manage tests. Let's see if there is one last thing I want to show is let's pick up a different test here. We looked at test templates. There is also a concept called graph templates. So if I right click on my graph and you can see everything is streamlined. So let's focus on the graph templates. Let's pick a graph template, apply a graph template. Let's go with a simple one called GXX, for example. So this is just a template that you apply on the graph, and it's very easy to make a graph template. You design and configure the graph the way you want it to look, and right click on it and save as graph template, and it will show up on this list. So if I go select a different one to add some color. So in this case, I have a tan color, and the FRFs are displayed in just magnitude instead of log mag. Go into graph templates again. Let's pick, because it's a transfer function, maybe a damping might be appropriate. And you can see that it's showing the top 10 peaks with the damping information on it. And just like the saves, I can go through the different saves to look at the damping. And back to the last one where we started with HXY report. So all of these are just annotations. So you can double click on them and you can configure, you can populate them from the available choices. Under the first tab, TRF, we have 4 graphs displayed here. We have a custom design tool that allows you to configure the page the way you want. For example, if I select this, so I have different distribution of the graphs. So this one is a little bit larger graph and this one are smaller graphs. And I can focus, I can move the graphs up and down using these arrow buttons, or I can also, for example, if I want to provide more emphasis on a certain graph, I can select 2 graphs and I can use the swap button. So I'm providing more focus on my transfer function. And I can simply go back to my auto, which gives equal weightage or equal distribution for all the graphs. The reporting tool is built into the software. So if I click on the quick report, I can select the portrait or landscape mode. I can select the number of graphs to display on each page and also include some of the parameters that are, the test is configured with. And if I click on report, it would create a report for us. Transfer function, what all the graphs that are displayed would be shown on the report, including the parameters as listed here. And once I have this report, I can simply take the information and I can make my PDF files or docx reports, or I can send via emails, PDF, and docx. All right, with that, I'm going to transfer it to Jim Steedman, who is going to talk about how all of these come together. Over to you, Jim.
Oh, thanks, Kalyan. Okay. Well, before we start, I would like to give a little background on Navcon Engineering. Navcon is a two-person noise and vibration consulting firm, and as Rob said, we're located in Fullerton, California. We started business in 1987, and we're in our 33rd year of operation. My background is in modal testing and analysis, and also structurally radiated noise. My associate, Hans Forschner, he really focused on environmental noise and noise modeling, and also architectural acoustics. And of course, over the last almost 30 years, we've kind of cross-pollinated there. Now, in addition to providing consulting services, we also train approximately 100 to 110 engineers and technicians every year. The courses that we have that are maybe more applicable to this webinar are our hands-on modal testing and analysis seminar and our validation and updating of finite element models seminar. And the third area of business that we have is product sales and hotline technical support. So we distribute MEscope, modal testing software, FEMtools, which is a software to kind of link test and analysis. When we also distribute hardware from Data Physics, APS, and some other companies. So Kalyan had demonstrated the 900 series GUI and also impact testing. What I want to do is talk more about impact testing applications. So impact testing, of course, is used to identify resonant frequencies. And from a troubleshooting standpoint, we make impact frequency response measurements, and we can compare them with operating spectra. And that helps us to determine whether a problem is more resonant related or whether it's a force vibration problem. We also use impact testing for health monitoring and quality assurance applications. And it helps us to determine whether resonant frequencies and damping values have changed over time, or maybe they change from part to part. And of course, if the resonant frequencies and damping values are changing, that means you have some structural anomaly in the test item. We also use impact frequency response measurements to do FEM-Test correlation. And kind of a lower level of correlation would be just to compare the resonant frequencies from test with those determined by analysis. Later on in the presentation, we'll show you more rigorous ways to do that. And then, of course, we have other vertical applications for impact testing. Now, 99% of all modal tests are conducted using impact testing methods because they're so easy to conduct. And we have for troubleshooting applications, we really want to see how a structure is bending and twisting as a function of frequency. We can also create these test models by conducting a modal test and then adding finite elements to the test model. And so if we're out in the field conducting and we have a vibration problem, we can say, well, what would happen if I put a rod in here, if we welded an I-beam here? And we can make some predictions using our modal test model as to how the resonant frequencies will change and how the mode shapes will change. And of course, we use modal testing data for FEM-Test correlation and the validation and updating of finite element models. And I will go into more detail on that. We'll do a demo on that. And modal results are also used for health monitoring purposes, the same way that we use just the impact measurements. So I just have a couple of quick slides here to show you some applications. In this case, we have a stage 3 compressor impeller. We have a laser vibrometer measuring the vibration response. We have a little mini hammer. and the output from the laser and the output from the hammer goes into, in this case, we're using a Data Physics Quattro. We measure the frequency response on each blade, and then we basically just superimpose them like Kalyan showed you in the 900 series software. And really what we're looking at is blade-to-blade variations in this case. And if we saw that some resonant frequencies are way out of line from the norm, then we might go back and inspect that particular blade. This was an application where we were testing 50 antenna bearings, and these antennas go on a military helicopter. And we want to make sure that the resonant frequencies do not coincide with helicopter resonance. That's shown with the brown, in the brown shaded area. We also want to make sure that we do not have resonant frequencies that coincide with harmonics of the gearbox rotation. And if you look at these little blue dots, that's where we find what we would call a pole of the system. On the vertical axis, we're plotting the damping value for each resonant frequency. On the horizontal axis, we've got the frequency itself. And you can see that the first resonant frequency for these 50 parts, they all kind of, form like a point cloud here, but we have some anomalies here. And in these three bearing assemblies, the frequencies are a little bit lower and the damping is a little bit higher. And so these bearings actually were rejected because they were kind of outriggers, if you will. And then this is the clump of the second resonant frequencies and then the third resonant frequencies. So this is kind of a quality assurance application. Now, the third application that I just want to show you is it had to do with a floor vibration problem. So there are about 200 cubicles on this particular floor. And as people would walk down the aisles, you'd have high vibration response at everybody's desks. And so the objective of the project was really to compare the vibration readings that we were getting in the different cubicles with a ISO standard, and then determine what was causing this, this excessive vibration. So in this case, this shows the vibration measurement recorded on the floor when people were walking. We've got peak acceleration on the vertical axis, and then we actually measured the vibration in third octaves. And in the 900 series software, you can be computing third octave band levels and narrow band vibration levels at the same time. In this case, we're looking at third octave band levels, and we've got the vibration response in 4 cubicles here, and then we also have the ISO guidelines here. So what we determined was that the vibration response in the cubicles exceeded the ISO standard between about 3 hertz and 9 hertz. And of course, the people that were in the cubicles didn't need a standard to tell you that the vibration was excessive. And then this is a narrow band vibration reading, and the blue is a vibration response measured in a cubicle, and then the black line shows the frequency response measured at the same point. So you've got, if you look at the block diagram here, of course, the green arrow going in, that would be the footfall induced vibration from people walking. The H function is the black line, that's a frequency response, and you can see that we've got resonant amplification here, and that results in a high vibration response at the cubicle desks. So for the remainder of my presentation, I really want to focus on what I call our integrated approach for modal testing, FEM-Test correlation, and finite element validation and updating. And I refer to this as an integrated approach because each of the products shown here, they just play very nicely with one another. And we have, on the front end, we use data physics analyzers. I think we have 6 or 7 of them in our lab. And then in the brown shaded area here, we've got our modal software, which we use as MEscope. And then the yellow shaded areas, that's the areas covered by FEMtools. And again, FEMtools really focuses on pretest correlation and kind of linking test with analysis. So let me start on the left-hand side in our flowchart. So we would begin with some design drawings. We develop a finite element model, and then we go through the eigensolution. And in the eigensolution, what we're really trying to determine are the resonant frequencies and mode shapes. And I have part of this box here shaded in yellow. because FEMtools actually has a Nastran solver built into it, or else you can use your external solver from your finite element code. But the result of this is a this dynamic analysis is of course, a finite element model with frequencies and mode shapes. And we can use that information to conduct a pretest analysis. And the pretest analysis is really an analysis to help us plan our modal test. So during the pretest analysis, we can determine where we need to be exciting the structure, either through impact or shakers, where our accelerometers should be, if our accelerometers are going to mass load the structure. If we're going to suspend a structure, where should we suspend it from so that we don't affect the modes or alter the modes of vibration? If we're doing a fixed boundary condition modal test, we can assess that fixed boundary condition too. And the output of that pretest analysis is actually a modal test model geometry, and that gets imported into the modal software. And we use that model geometry during the modal data acquisition here. And again, although this is a small blue box, you know, when you open it up, there's a lot of little boxes in there. But we acquire the modal test data, and then we export it to our modal software. And in the modal software, again, the brown is really kind of the MEscope part, but we also have a yellow part in here because FEMtools also has parameter estimation. And I would just say here that MEscope is a true modal testing software package really intended for the test engineer. And FEMtools, it kind of overlaps the finite element side and the test side because it does certain tasks on both sides, but it really is focused on the center section, which is, again, correlating the FEM and test models and then updating the model if the FEM and test models do not meet your correlation criteria. So again, as far as correlation goes, we import the frequencies and mode shapes from the test, we import the frequencies and mode shapes from analysis, and then we usually with dynamic correlation, we're looking at how do the frequencies line up and how close are the mode shapes. And if we meet our correlation criteria, then we're done. If we don't meet that correlation criteria, then within FEMtools, we can actually go through a model updating process. And I'm going to show you that here in a little bit. But the other thing I would just say is that we should also look at this other path that, hey, maybe you didn't do something right in the modal test. You should always go back and look at your modal test results. Maybe you need to go through the parameter estimation process again. Maybe you need to redo the modal test. So in the next kind of hands-on or the demonstrations, we're going to be using Jim Beam. We built Jim Beam back in 1991 for our first modal testing seminar, and Jim Beam was used in the IMAC round robin in 2009, so it was tested by consulting firms across the country, I think some in Europe too, to kind of compare results, see if everyone was getting the same results. But Jim Beam has 3 aluminum plates. They're bolted together. The top plate's bolted together to the side plate, as is the bottom plate. And there are provisions so that we can add structural modifications to this. We can add rod stiffeners, springs, masses, etc. And then we can model that using structural dynamics modification techniques, both in MEscope and FEMtools. So this is really a laboratory test item. And here we're just showing impact test. This is the accelerometer that we typically use for Jim Beam. It's a 1 gram triaxial accelerometer. And this is one of our attendees that came from Australia. I think he's been in the class a couple times. So later on, when we look at FEMtools, we're gonna import into FEMtools a 3D kind of brick model using hexate elements of Jim Beam, and then we're going to correlate that with test results. So with that, what I'd like to do is just show you, kind of do a brief overview of MEscope. MEscope is primarily used for modal testing and operational deflection shape testing. It's also used during frequency response surveys and operational surveys. And also it has, you can do sound pressure tests, sound power tests, acoustic intensity tests, and that's all kind of built into FEMtools. Now, this is let me find my cursor here. This is a modal testing model. Of course, it's much simpler than a finite element model. In modal testing, most modal tests are conducted with maybe as many as 10 response locations, up to maybe 300 or 350. That would be considered a pretty large modal test. And the modal test model, you open this up, it's basically a stick model. And so you have points. So you have to put in the X, Y, and Z coordinate of every test point on the structure. And let me just show you the test points on Jim Beam. In Jim Beam, we have 39 test points. We usually measure the response in all three axes, so that results in a total of 117 frequency response measurements per test. In addition, in the model, you've got to connect the dots, so we have lines that do that. You can also add surface triangles and quad surfaces, so as you're animating the modes of vibration, if you'd like to look at color contours and look for node lines, you can do that. Now, in this same menu, this is where we would add finite elements to our modal test model. We can add springs and masses and dampers and everything to kind of predict what will happen if we make these modifications. Certainly, this analysis is not as rigorous as a finite element analysis, but it does give you some good trends, and it's a great technique to use in the field. Now, as far as developing these models, we can, of course, input the finite element. We can import the test model directly from FEMtools. So from the pretest analysis, we just import it into MEscope, and it's up and running. We can also generate these test models within MEscope, and MEscope has a mesh generator. And you can also go old school and just type in the X, Y, and Z coordinates of every test point. We can also develop test models using photo models. We use a program called Photo Modeler out of Canada in our lab. And what you can do with this is you can basically use a digital camera. You can take pictures of your test item from multiple directions and then morph those pictures together, and you'll come up with a test model like this. And then you basically tell the test model where you're going to be making your measurements. And you can see here that this model was it's actually a picture of Jim Beam SN number 60. So this is the 60th Jim Beam that was created. And now with that, what I would like to do is to import some test data. So this data was already acquired using the Data Physics Analyzer. And I'll just go File, and I'll import a data block. We're going to import all 117 frequency response measurements. And I'll create a new file and just call it FRS. And now at this point, what I typically do is I will kind of zoom in the data block. I'll use a magnifying glass, kind of zoom in, and we can go format and overlay all of the measurements in the data set. We can put up a cursor. I used to prefer to use the split cursor, and what that's going to do is it's going to pick off the maximum amplitude of the frequency response between those two cursors. And I can come over to the structural model and then just animate it. And again, we haven't gone through the analytical side of this, but if you're going to do this type of animation for frequency response data, that's acceleration over force, we typically look at the imaginary part of the FRF and animate that. And then we can just slide these band cursors around to the different peaks. And if the modes of vibration are separated by a wide enough frequency band and you don't have coupling between the modes, these are the mode shapes. You can't do better than this. If the modes of vibration are more closely spaced and you get coupling, then we'll have to go through a modal parameter estimation process to extract the modal parameters, which, as Kalyan said, are frequencies, damping, and mode shapes. So here I'm just going to do a quick parameter estimation on this data. I highlight the data block, go under curve fit, and say open curve fitting. Now in MEscope, the parameter estimation is actually a three-step process. In the first step, what we do is compute a mode indicator function, and this will this mode indicator function. Let me just go ahead and compute it. We'll say count peaks. And that will give us an indication of how many modes we have in that frequency band. And whatever algorithm we select to compute the frequencies and damping, it needs a starting estimate as to how many modes there are and kind of where these modes are located. And in terms of the mode indicator function, MEscope has the CMIF and MMIF methods and also multi-reference versions of them. Now, in the second step, what we want to do is to get an estimate of the resonant frequencies and damping values. And if you recall the frequency response equations, the denominator of the equations is related to the poles of the system, which are frequencies and damping, and the numerator is the residue, and that's related to the mode shape amplitude. So basically, we're solving for the characteristic equation here. We have different methods for determining the resonant frequencies and damping values. They have polynomial methods, global, polynomial, local, and multi-reference. They've also implemented several stability methods. So we've got AF poly, complex exponential, Z poly, and multi-reference versions. For this demonstration, I want to make it very quick, so I'm going to go ahead and let's see. Sorry about that. I missed one of the peaks I wanted to fit here, so let me just move down here, recompute the mode indicator function. And now we'll go ahead and use the polynomial curve fitter to get the frequencies and damping. So I'll just click on that. I'll say yes. So it comes up with 7 resonances. This part of Jim Beam is very easy data to fit. So you can see in the table below, we've got the frequencies, we've got the damping in hertz and the damping in percent critical. In the third step, we're going to compute the residues or the mode shape amplitudes. This is kind of solving the numerator of the frequency response equation. And we've got different methods to fit the mode shape amplitudes. We're going to use a polynomial method, and I'll just say compute the residues and say yes. So after it's done fitting the residues, I'm going to go ahead and look at each individual measurement. We can kind of look at it in a magnitude format. And the black line you see here, that's actually the measured data. The red line is a synthesized frequency response function based upon the frequencies and damping extracted from the modal data and also the residues that it extracted. And we can scroll through the different measurements and kind of look at our curve fits. And you can see that this mode here, number 4, is not all that great. It's not fitting the data. So probably we would want to, or very definitely we would want to use a different parameter estimation method and see if we can get a little bit better fit on that. So at this point, we've got the first 7 modes. I'm going to save the mode shapes into a new file, and I'll just call it poly because we used a polynomial method to get the frequency and damping. We also used a polynomial method to get the residue. So we'll put that there, and now we can just animate these modes of vibration. I'll click on the first mode, and let's go ahead and animate. So that's the first mode of vibration, the second mode, third, fourth, fifth, and we can look at those. And of course, MEscope's got a lot of different animation tools and the way you can look at data. But at this point, once we've finished our modal data acquisition, we've gone through the parameter estimation process, the next thing we would want to do is to export the model geometry back to FEMtools and also the mode shapes. And this is a very easy process. So I highlight the structural window and I say File, Export the structure, and I can just export it. And we typically export in a UFF file format that can be read by FEMtools. We can do the same thing with the shape table. So we'll go File and Export Shapes, doing the same thing. Now, what I want to do is do a quick switch over to FEMtools. And like I said, FEMtools is really a software package to link the test and the analysis. And what I'm going to do first of all is I'm going to import our test data. So we'll go Import Test Model and Shapes. And I've got MEscope Jim Beam Test Model Geometry. So we'll import it, and that's actually what we saw in MEscope 2. And I'm going to import the MEscope mode shape. So we'll go Import Test Model and Shapes. I'll click on the mode shapes from Jim Beam, and then we can animate these. And you can see here that we've got 15 mode shapes here, 15 modes of vibration, and we can just kind of scroll through those. Now, in the next step, what I'd like to do is I'd like to import a finite element model. So we'll go File, Import, FE Model. And in this case, I want to import a kind of a 3D brick model of Jim Beam. And at this point, we could import the modal results, frequencies, and mode shapes from our finite element program, or we can compute those within FEMtools. So I'll do this one in terms of FEMtools, and I'll say Tools, Modes Analysis, and I can select the solver I want to use, FEMtools, Nastran, whatever you have available on your computer or your network, and we're going to compute 15 modes of vibration, and I'm going to set a minimum frequency of 1 Hertz because I do not want to compute the rigid body modes. Jim Beam was tested in a free condition. So we'll say OK. Takes a few seconds to compute these modes, and then we can animate them. So there's mode number 1, mode number 2, etc. And we can go through all the modes. So the next step, what we want to do is we want to correlate or look at the correlation between our finite element model and our test model. So I've superimposed both models on top of one another. And the first step of the correlation process is to link every test point with a specific node on the finite element model. To do this, we simply go Tools, Correlation, Node Point Pairs. And so now we could zoom in and we'll see there's actually like a little green line that goes between the test point and the finite element node. The next step is that we have to correlate the degrees of freedom that were measured. And during the modal test, we had a total of 39 test points. We measured the response in 3 directions, so that's a total of 117 degrees of freedom that we measured, and that's shown up in the table. The last step, to correlate the models, we go Tools, Correlation, and we can go Mode Shape Pairs, and we'll go ahead and pair the mode shapes. So on the table on the right-hand side, that's a result of our correlation. So you can see that we have 15 pairs of finite element modes and test modes. And in the second to the last column, this shows us the correlation in frequencies. So the first mode, the FEM mode was 58.4, the test mode was 63.1, and there was a 7.4% difference. The MAC values, if we look at the mode shape, the MAC value was 99%. The MAC value is very similar to the coherence function in frequency response testing. We want a MAC value of 100, which means that we have identical mode shapes. From a correlation standpoint, typically we try to get the MAC value between test and analysis to be greater than 90%. And here we've got greater than 90% for all the modes. But the issue that I see here is that the FEM frequencies are a little bit lower than the test frequencies. So we're going to go through a quick model updating process, and we'll try to improve that frequency correlation a little bit. One other graphic I do want to show you is the 3D MAC matrix. And this matrix, this is showing the MAC values between the FEM and the test. And you can see we have very high correlation. So the values along the diagonal are these values in the graphic. So in order to update the finite element model, the models are now correlated. We want to update it, so we'll go. In fact, we'll put the frequency pairs here, and then we've got the mode shape pairs over here. And in this graphic right here, of course we would want that to be a straight line if we have the same frequencies. So we'll go Tools, Model Up. Oh, sorry, I skipped a step. In order to do the model updating, we're going to need to select targets for the updating, and we're going to use the modal results from the test. We're going to use the 15 resonant frequencies and the MAC values. And so this will be the target for correlation. So we want the finite element model to match the frequencies from test, and we also want to get the best possible MAC matrix that we can get. We also have to tell the system what parameters of the finite element model we want to update. And in this case, I'm going to select Young's modulus, or the modulus of elasticity, for every individual brick element in the finite element model. So we'll look at the elements in the bottom plate, the top plate, and the side plate. So we've got a total of 15,300 elements that we're going to try to update, and we've got the 15 frequencies and the 15 MAC values. So now we'll go through the model updating process. I go Tools, Model Updating, and we'll just do an automated method. And in the updating process, we'll do 10 iterations. And we're going to say we want the frequencies to be within 0.1%. We can do that. That'd be pretty good correlation. And the maximum parameter change, the maximum change in modulus of elasticity for any brick element in any iteration will be limited or capped at 25%. So now we'll start. And as we're going through the model updating process, you can look at the changes in frequencies as we're going through the model updating. You can see the correlation is getting better after 2 iterations. Now we're at 3 iterations. And at 4 iterations, we've now met the goal. The average difference between the frequencies is 0.099%. We specified it at 1%. Yeah, 0.1%, I guess. And this is where it modified the modulus of elasticity of the different elements. And what's interesting is that it modified those elements where we have the steel bolts bolting the top plate and the back plate and or the side plate and the bottom plate and the side plate. So kind of, I just want to summarize this. So in summary, we kind of looked at some impact testing applications where you might want to just take impact measurements and kind of evaluate the frequency response functions. We looked at modal parameter estimation in MEscope. We also looked at how we can correlate finite element and modal test models. And we also went through a model updating process.
Thank you, Jim and Kalyan, for that excellent presentation and demonstration. This concludes our live webinar on modal analysis, impact testing with the Data Physics 900 series analyzer and more. Thank you all for attending and for your participation.